Hello YouTube! In this video I'm going to explore some of the conceptual challenges associated with replication of scientific experiments. Replication is of course a fundamental aspect of scientific activity. Indeed, replication is generally thought of as the sort of gold standard of scientific experiments. One of the distinguishing features of science is that if an experiment reveals a genuine effect, then this effect should be replicated when the experiment is performed again. As Karl Popper once put it, and I quote, "We do not take even our own observations quite seriously or accept them as scientific observations until we have repeated and tested them. Only by such repetitions can we convince ourselves that we are not dealing with a mere isolated coincidence, but with events which, on account of their regularity and reproducibility, are intersubjectively testable." So the point is that we should recognize particular results as data against which we test our theories, only if those results can be replicated. And this, of course, is why the replication crisis is so troubling. In many scientific fields, it turns out that a high proportion of results fail to replicate, and this undermines the theories that are built on those results. But what exactly is replication? And what is required for an experiment to be replicated? At least initially, it seems straightforward. We might say, well, look, a scientist who performs an experiment will describe the equipment, the apparatus, the materials, and the experimental method, and then other scientists can construct the same equipment, they can use the same materials, and they can perform the same method, and then they can see if that gives them the same result. An experimental result can be replicated just in case anybody who has the same equipment and anybody who has learned the experimental technique can achieve the same result. That's the basic idea, but it turns out to be very difficult to apply this idea in practice. So what we're going to do today is just look at some of the kind of wrinkles that occur in practice with trying to apply this idea. And I'm drawing here in particular on Harry Collins's book Changing Order, particularly chapter 2, which I think provides a very good introduction to some of these difficulties. So a first point to note is that there are, broadly speaking, two different kinds of replication. So first of all, there is what we might call direct replication, or repeatability of results. So to say that a result is repeatable is to say that this same result will be obtained when precisely the same experimental conditions are in place. So this involves an exact replication. Ideally, we would have the same apparatus, the same materials, the same researchers, the same test procedure, and so on. Now in practice, this ideal is often impossible to achieve because performing an experiment on a particular sample may alter the sample. Like if a scientist tests the effects of a chemical on a plant cell, then the chemical may alter the cells that they use. So, performing exactly the same experiment again is just not possible, right? Like we don't even have the same materials. But like a direct replication tries to conform to the original experiment as closely as possible. Second, there is what we might call conceptual replication or reproducibility. To say that a result is reproducible is to say that it reappears under changed conditions. So when aiming to reproduce a result, we explicitly aim to vary the original conditions of the experiment. The second experiment will be performed by different researchers, it will involve different equipment, it may use a completely different procedure, a procedure that uses different theoretical principles. Now, there isn't going to be a strict distinction between direct and conceptual replication. The point is just that sometimes scientists will aim to remain as close as possible to the original experiment, and sometimes they're going to aim to vary the experiment while aiming for the same result. And there's an interesting tension between direct and conceptual replication. Because, so one thing to notice is that in most cases, an exact replication of an experiment is not really going to be that interesting. Indeed, if the second experiment is exactly the same as the first, then we already know it's going to produce the same result, at least if we, ignore like metaphysical indeterminacy, quantum indeterminacy and so on. Clearly if the experiment is exactly the same, it's not clear how we're going to get any new information from performing it again. There may be some value to an exact replication because it might help to rule out fraud and so on, but putting that aside, it's not obvious what you would get if you were able to make the conditions exactly the same. Now let's say we start varying the conditions. So we might run an experiment and then we perform a very similar experiment a few minutes later, like we perform it at a different time. Well, that's going to provide some additional confirmation, though not much. Let's vary some more factors. So we don't just perform the experiment at a different time, we have it performed by a different experimenter. Or we alter a part of the apparatus, or we construct a completely different piece of apparatus based on different theoretical principles. If, under these changed conditions, we keep getting the same result, that is going to give us additional confirmation of that result. It will show, for example, that the result is more than just an artifact of the particular piece of equipment that was used. So, by varying the experiment, it looks like we confirm the result. But of course, this variation, the power of variation only goes so far. So here's a nice example from Harry Collins. Let's suppose that a team of scientists using a laser interferometer declare that they have detected gravity waves. And then this result is confirmed by a second team. But it turns out that this second team is a group of fairground entertainers who have achieved the confirmation by reading the entrails of a goat. Well, I mean, in this case we have enormous differences between the two experiments, but this second experiment has no confirmatory power whatsoever. In fact, we wouldn't count that even as an experiment, right? So that's not going to count as a legitimate replication. So what we can see here then is that as differences between the original experiment and the replication increase, confirmatory power increases, but then too much difference leads to a decline of confirmatory power. There's some optimum point somewhere in the middle. Unfortunately, there are not any clear rules for determining where exactly that optimum point is. It's likely to be different in different contexts. So what we can already see then is, okay, we have these sort of two different approaches to replication, and there's not a clear boundary between them. There is some tension between them. This still leaves us with this more general question of what constitutes a replication at all. So consider an experiment with some result R. Our question is, how do we decide whether or not R has been replicated? And Collins argues that there are at least 7 steps involved in coming to this decision. So I have the 7 steps here. We will examine them in a little more detail, but just to go through them first. So first of all, we have to specify the activities that have to do with the subject of R. Then of the remaining activities, we have to eliminate all those that are not scientific. And third, of the remaining activities, we eliminate those where the identity of the experimenter is inappropriate. Fourth, of the remaining activities, we eliminate those that are not experiments. And then fifth, we eliminate all experiments that are not competent copies of the original. Sixth, we decide whether the result of those experiments is positive or negative. And then 7, we decide whether R has been replicated. So what we're doing here is, we can kind of imagine like a particular research team performs an experiment and they claim to have result R. And then we want to know when this result has been replicated. So imagine we begin with all human activities and then we start sorting them. We start sorting them into different categories with the ultimate aim of deciding which ones count as replicating R. And it turns out that at all of these steps, it's very difficult to specify clear rules for making a selection. So yeah, we'll look at each of these steps and look at some of the difficulties that arise. So step 1, we have to specify all the activities that have to do with the subject of R. Well, generally this is straightforward, but especially in new or in controversial domains, the exact boundaries become unclear. Collins, for example, cites research into psychokinesis. The defender of psychokinesis might say that deliberate bodily movement counts as a kind of psychokinesis because deliberate bodily movement involves the control of bodily matter by the mind, right? So the point of psychokinesis is that you have like this mind substance that can control matter. Well, hey, deliberate bodily movement, right? We're controlling bodily matter by the mind, so that counts as part of the subject. I mean, the question is here, like, which activities are related to psychokinesis? And it looks like we can't really answer that question until we have a theory of whether or not psychokinesis occurs, and if so, what its mechanism is. But of course, to get a theory of psychokinesis, we first need to perform experiments related to psychokinesis. But then we can't say which experiments are related to psychokinesis until we have a theory of psychokinesis. So we seem to be caught in a bit of a circle here. Similarly, consider research into the origin of life. Suppose a scientist claims to have spontaneously generated life in a laboratory environment. Well, that raises the question, what exactly is life? There are many life definitions that are taken seriously by biologists. Generally speaking, biologists define life in terms of cells that undergo metabolism to maintain homeostasis. On this definition, viruses and prions do not count as life because viruses and prions are not cellular. But that's very controversial. In fact, there are a whole bunch of different life definitions, and some of them would count viruses and prions. So, if we ask, like, well, what are the activities that are related to the origin of life, right? Or like that are related to, that have to do with the subject of origin of life research? Well, it depends on what counts as life. And that's controversial. Now, in practice, step 1 doesn't really pose too much of a problem because in the context of experimental replication, scientists are explicitly attempting to talk about the same phenomenon. When one scientist claims that an experiment is a replication of another, both the supporters and the critics will almost always agree that they are at least talking about the same topic as the original experimenters. But even at this step, it's not just obvious how this agreement is secured. It would certainly be possible to kind of raise objections here. But let's say that we have been able to identify which activities are to do with the subject of R, and then we move on to step 2. So in step 2, we aim to eliminate all activities that are not scientific. So of course, reading goat entrails doesn't count as the replication of an experiment because reading goat entrails is not a scientific activity. It's not part of science. Now, of course, in order to apply this step, we need some sort of demarcation criteria to distinguish science and non-science. Turns out to be very tricky to specify what this criteria are. So there's a great deal of debate about what exactly it is that distinguishes science from other practices. I'm not going to go into this in any detail here, but I have a series on philosophy of science which examines some of the approaches to the demarcation of science from non-science. So I'll link those videos in the comments. But yeah, I mean, like, this demarcation problem is one of the central topics in philosophy of science. It remains unclear how best to answer it. So in our attempt to distinguish activities that are not scientific from activities that are scientific, well, we're gonna face some problems. But let's say we can do that, and then we move on to step 3. In step 3, we eliminate all activities where the identity of the experimenter is inappropriate. Now, we might question whether this step is actually important. It might be argued that the identity of an experimenter is always irrelevant. I suppose it's part of the sort of mythology of science that science aims for objectivity, that science is defined in terms of its method, a method that, in principle, anybody can follow. So it shouldn't matter who is performing an experiment. Right? All that matters is what's the method that they're using. But a thing to notice here is that there may be little or no confirmatory power in an experiment that is replicated by the same experimenter or by members of the same research team. So suppose, for instance, that there's a research team who claim to detect a surprisingly high flux of X-ray radiation from a particular star. This team then runs the experiment again and reports the same result. Is this a replication? Well, it probably wouldn't be considered a replication. It would instead of counting this as a replication of the first experiment, we would probably count it as simply the second run of that experiment. So if we think about how these results would usually be reported, a team of scientists might perform several runs of an experiment, but then they would publish a single article, and they would take the data from all of these runs as their set of data, as a single set of data. So, the team might collect data from the star on several different days, and then they'll present this in a single report. That would not usually be considered several replications of a single experiment. Instead, all of these runs count as contributing towards a single result. The result here would be the detection of the phenomenon of X-ray flux, and we only have a replication of that result once a different team is able to detect this X-ray flux as well. But if it's just, like the same team using the same equipment on, another day, well, usually that would not be taken to be a replication. So the identity of the experimenter it seems can be inappropriate, right? Like sometimes in virtue of the identity of the experimenter, we may say this doesn't count as a replication. So we need to focus on those activities where the identity of the experimenter is appropriate. Okay, let's say that we have figured out a way of identifying these activities. Then we come to step 4. In step 4, we have to eliminate all activities that are not experiments. Of course, this raises the question, what's an experiment? And this is a surprisingly difficult problem. The basic issue here is that in setting up any experimental apparatus, or in performing any kind of empirical study, it's often extremely tricky, right? Scientific instruments often fail to work properly the first time they are operated. Empirical studies often run into unforeseen obstacles, and this presents particularly difficult problems in contexts where little is known about the phenomenon under study, or when we are designing new instruments to probe into previously unexplored domains. In these cases, even minor changes to the experimental apparatus can have significant effects. So Harry Collins quotes a scientist who was working on the construction of instruments for detecting gravity waves. This was back in the 1980s, before we had reliable instruments for doing that. So what made the detection of gravity waves so tricky is that it just wasn't obvious what was actually required to have a reliable detector. That there were proposals that so there were some scientists who claimed to have detected gravity waves, and then other scientists were trying to replicate their findings. And they say that one of the problems with this is, and I quote, it's very difficult to make a carbon copy. That is a carbon copy of the original instrument. You can make a near one, but if it turns out that what's critical is the way he glued his transducers, and he forgets to tell you that the technician always puts a copy of physical review on top of them for weight, well, it could make all the difference. So another scientist comments as follows: when you are working with and trying to get the most out of things, you will find that, for instance, a tube you've selected, say 1 out of 100, only stays good as a noise tube for a month if you are lucky. Something happens, some little grain falls off the cathode, and now you've got a spot that's noisy, and the procedures for finding this are long and tedious. Meanwhile, your system to the outside looks just the same. So lots of times you can have a system running, and you think it's working fine, and it's not. He summarizes: any small difference in the apparatus can make a big difference in the observations. So the point is then is that, look, let's say that, scientist A claims to have detected gravity waves. Scientist B comes along, tries to construct an apparatus for making the same detection, and scientist B is unable to confirm the original result. But then it turns out that the reason why scientist B is unable to confirm the original result is that, a grain has fallen off the cathode, and, there's some spot that's noisy and it's messing with the data, right? There are so many ways that these instruments are so delicate, there are so many ways they can go wrong, that it just isn't clear when we have a functioning instrument. So as a result of this problem, any competent experimenter is going to perform a number of preliminary tests before performing the experiment itself. And it may be that a great deal of tinkering is required in order to actually set up the experiment. So whenever we find, a scientist using a piece of apparatus and getting a result, or performing an empirical study and getting a result, we need to ask, what counts as a legitimate experiment versus a mere preliminary run? So if a team of scientists report a surprising result, another team tries to replicate this result, the second team will only report their data once it's the outcome of an experiment. But how do the second team decide whether they have actually performed an experiment or merely a preliminary run? This problem presents some serious difficulties for statistical science. There's a well-known problem of publication bias in science. So there is pressure on scientists to publish positive results because null results are simply less interesting. This is sometimes called the file draw problem, where scientists perform experiments, they get negative results, but these results just aren't published. They are left in the file drawer. This is a problem because it means that in the literature there is a bias towards positive results, a misleading bias. Since we can expect that at least some studies will find positive results merely by chance, the failure to publish negative results presents a misleading picture of what the facts are. But a complication here is that it can always be argued that a negative result is due to some mistake on the part of the experimenter. So there's a failure to construct the apparatus correctly, or a failure to correctly control confounding factors. And in that case, it isn't really a problem that the results are left in the file drawer. That's actually where they should stay, because if we count the negative results of a faulty apparatus, or we count the negative results of a poorly conducted study that has failed to properly control confounding factors, well, that would obviously be a mistake, right? So when one research team reports a positive result, another team tries to replicate the result but fails, that failure doesn't really tell us anything if the failure to replicate their result is because of error or incompetence. We need to, in step 4, the point is we have to decide, are we dealing with an experiment or merely a failed preliminary run? And it really isn't at all clear how we objectively draw the line on this one. Okay, so now we come to step 5. Eliminate all experiments that are not competent copies of the original. So to see the problems that we face at this step, let's consider one of the classic cases of failure to replicate a result. So in the mid-90s, the psychologist John Bargh reported a priming effect where reading words associated with the elderly seemingly made people walk more slowly. So in his experiment, undergraduates were given sets of scrambled sentences and were asked to make those sentences sensible. And after performing this task, the undergraduates were sent away, and researchers measured the speed at which they walked down the hallway. In one group of undergraduates, the sentences contained words associated with elderly people. In the control group, there were just random words. Now, the subjects in the group who were given the elderly-related words walked significantly more slowly down the hallway than the control group. So it seems that reading words associated with elderly people primes people to think about the elderly, and this somehow makes them act in ways associated with the elderly. Thoughts about the elderly, for some reason, affect our behaviour. Now, a number of subsequent studies have attempted to replicate this result, but have found no difference in walking speed. So now it looks like the priming effect might be spurious, at least in this particular case. This particular case of behavioural priming has become one of the classic examples of the replication crisis. But there's an interesting defence of the Bargh study, which, to be clear, I'm not endorsing this, but it's just a good illustration of step 5. This comes from Michael Ramskar. I will link an article by him in the description where this argument is outlined in much more detail. But basically the point is this. Bargh's initial experiment was run on English-speaking undergraduates from an American university. It was conducted in 1991. Now, an immediate point to notice here is that since 1991, language has changed in some ways. Indeed, the whole culture has changed. The way that we think and talk about elderly people is different today. The way that we interact with others in general is different today. I mean, think about the impact of the internet and social media and so on. So, there are lots of differences. And with this in mind, it's maybe not surprising that what looks like the same experiment would actually have different results. In some sense, it might not be possible to replicate the Bargh study because the culture that he was sampling from no longer exists. So we might think, if we want to find a priming effect, we might well need a different procedure, right? Like, it may be that the changes in language and culture and social interaction and so on actually undermine that effect. So even if that effect is real and Bargh's experiment did reliably identify an effect, it's not obvious that this effect would still manifest. In fact, there are actually potentially serious problems with some of the attempted replications of Bargh's study. So one famous case of failed replication was a study by Stephanie Doyen and colleagues, reported in the article Behavioural Priming. It's all in the mind, but whose mind? So this study attempted to replicate Bargh's study, failed. However, this study, Doyen's study, was performed on French-speaking students who were given a set of French translations of the original elderly-related adjectives. And Ramskar points out that the frequency of these adjectives varies considerably across the two languages. For example, here is a chart which shows how often nouns occur after the adjectives in question. And with one exception, English speakers have far more exposure to all of these words. So the English adjectives are in blue, the French in red. And you can see that, with just one exception, there's more exposure among English speakers to these words. So even if the priming effect is real, we might argue that we shouldn't expect it to manifest in exactly the same way when studying a different culture that used a different language. It looks like Bargh could legitimately object. it's entirely to be expected that this second experiment failed to confirm the priming effect. The second experiment wasn't a competent copy because, the words they were using, there's far less exposure among the subjects to the words that they were using. Okay, so much of the debate among scientists concerns whether or not experiments have been competently performed. And this is where the kind of naive view of replication really comes under pressure, because there just aren't any general rules for identifying whether or not an experiment has been competently performed. Our judgment of whether an experiment has been competently performed can depend on very subtle background facts. So, considering Barger's priming effect, it's not obvious what should count as a competent experiment. Do the differences in degree of exposure to a word actually matter? Well, maybe not. French speakers may not be exposed to the word vieux as often as English speakers are exposed to the word old, but presumably both of these words evoke similar associations and concepts and feelings. So if there is a priming effect, shouldn't both of these words prime behaviour in a similar way? Why would it matter how often people are exposed to the words? On the other hand, maybe it does matter, right? In order to determine whether or not Doyen's study was a competent copy of Barger's, we need to know whether degree of exposure to a word would make a difference to the priming effect. But we won't know that until we know whether or not there is a priming effect, and if so, how exactly it works. What exactly is the mechanism by which this works? Or, what's the mechanism by which it would work if it existed? Different scientists will make different assumptions about this, and these different background beliefs will dictate whether Doyen's study is judged a competent copy. So the kind of background assumptions that scientists are making are going to dictate whether they judge Doyen's study to be a competent copy. Unfortunately, there aren't any just kind of clear-cut general rules that can be applied in these sorts of cases. Okay, so let's say that we do have, let's say that we are able to identify which experiments count as competent copies. Well, now we need to decide whether or not the result is positive. So we have a set of experiments. We need to divide them into those which have positive results and those which have negative results. So what exactly is a positive result? Well, one area where there are complications here concerns the level of statistical significance. In the social sciences, the 5% level is commonly used. So a result is counted as positive just in case the probability of its arising by chance is less than 5%, less than 5 times every 100 trials. So there's a less than 5% probability of finding an effect even when no effect is present. Now, of course, the exact level of statistical significance that we choose is going to be arbitrary. Why 5%? Why not 3% or 6% or whatever, right? Moreover, the exact level of statistical significance that we choose will be influenced by a variety of factors. The conventions prevailing in the field, our values with respect to the hypothesis being tested. So if we claim that there is a priming effect due to reading words associated with elderly people and we're wrong, well, that's not a big deal. That's not going to have any negative consequences. At least probably not, right? So we might well be happy with a 5% level when testing that hypothesis. On the other hand, if we are testing whether or not a particular chemical has carcinogenic effects, the negative consequences of error in that case could be very great. So in that case, we demand a higher level of statistical significance. Our attitudes and values with respect to a hypothesis will dictate the level of statistical significance that we choose. And that's going to dictate whether or not we count the experiment as having a positive result. So check out, I have a video on values in science in which I talk about this point in a lot more detail. Again, I'll put a link to that in the comments. So check that out if you're interested in more on that point. Another point here is that, as with the previous step, judgments about whether an experiment has a positive or negative result will depend on our background beliefs. So consider, for example, Dayton Miller's attempt to replicate the Michelson-Morley experiment. Briefly, the Michelson-Morley experiment was an attempt to detect a substance known as ether. The ether was proposed in the 19th century as the medium through which light waves travel. It's supposed to be a sort of a very subtle substance or field that occupies all of space and through which the Earth travels, and this is the medium that propagates light waves, and this is why we can. I mean, on this theory, this is why we are still able to see lights even through a vacuum. So it's like light is a wave; it propagates through this medium, and this medium just permeates all of space. Now, since the speed of light should be constant with respect to the ether, the prediction was that light waves travelling in the same direction as the Earth's movement through the ether should have a different speed to light waves travelling at right angles to it. The Michelson-Morley experiment aimed to confirm this prediction. So here's a basic description of the experiment. We have light is beamed at a half-transparent mirror that splits the beam into two perpendicular paths. So we have beam A that continues to the mirror on the right. Beam B is reflected up to the mirror on the top. Both A and B are then reflected back. Some of beam A will be reflected by the half-transparent mirror. Some of beam B will pass through the half-transparent mirror until they both reach a screen at the bottom. Now, if there is an ether, the beams A and B should travel at different speeds, so they should reach the screen at different times. The Michelson-Morley experiment tried to find this. They tried to find this effect of the light beams reaching the screen at different times. They failed. They found no evidence of ether. And their failure to find this evidence played a very important role in the development of special relativity. So yes, this was a significant experiment. The failure to find this effect was important. But in 1926, Dayton Miller, using equipment that was far more sensitive than the original Michelson-Morley apparatus and using elaborate precautions to eliminate possible sources of error, reported a positive result for this ether drift, as it was called. There were many criticisms of Miller's experiment. One important criticism, however, was that Miller's results didn't actually confirm the predictions of the ether theory. This objection was raised by Hans Thirring, for example. So the problem here is that the ether wind, as it were, as the Earth moves through the ether, that will create ether wind. This ether wind will come from one direction in space. And so as the Earth rotates, the direction of the ether wind detected by Miller's apparatus should similarly rotate. Like if you imagine blowing wind onto a globe onto which a wind vane is attached, then as the globe rotates, the direction the wind vane points with respect to the surface of the globe will change. But examining Miller's data, Thirring was unable to find this effect. Instead, he found, and I quote, "What actually happens is the occurrence of an effect pointing towards the northwest quadrant of the compass in about 95% of all observations. This fact seems fatal to the assumption of an ether drift of constant direction towards a certain point of the heavens." So, is this a positive result for the ether theory or not? Does Miller's experiment count as a detection of the ether? Well, I mean, on the one hand, if there is no ether, you wouldn't expect Miller's experiments to detect anything. And certainly, I mean, if we take Miller's experiments seriously, then they present a prima facie problem for special relativity. On the relativity theory, the light should reach the screen at the bottom. So both beams of light should reach the screen at the bottom at exactly the same time. And that wasn't what Miller found, right? Miller found that they did reach it at a different time. So that seems like maybe it is a positive result. On the other hand, if we treat Miller's result as a positive result, then it seems we're going to have to significantly modify our theory of how the ether works. And that isn't necessarily a problem, right? I mean, maybe there is an ether, but it's just that the ether behaves in unexpected ways. The point here is just that our background beliefs about how the ether operates and our willingness to make adjustments to the ether theory versus simply eliminating the theory, like how willing are we to, work out how to modify the ether theory so that Miller's results become expected, right? Like, that's going to dictate whether or not we count Miller's result as positive or negative. And, again, there aren't really any clear rules for making this determination. Okay then, so finally we come to step 7. Decide whether or not result R has been replicated. So we have a set of experiments concerning R which have been performed by competent experimenters and for which we have assigned either a positive or negative result. Even at this stage, however, there may be complications because in practice we will sometimes have a mixture of positive and negative results. One reason for this is that no matter how competent an experimenter is, it may be that the phenomenon under investigation is expected to fluctuate or is only probabilistic. Suppose, for example, that there is a research team who claims to detect a biosignature molecule in the atmosphere of another planet, such as when it was claimed that phosphine was detected in Venus's atmosphere. Well, we might well expect that whatever processes produce phosphine would vary in intensity, or perhaps there will sometimes be other processes at work that will destroy the phosphine, and those processes will vary in intensity over time. In which case, we should not expect that all subsequent studies would reveal the phosphine, right? So actually a mixture of positive and negative results would be entirely expected there. So, again, like our judgment, the judgment we make when we face this mixture of results kind of depends on our background beliefs about the phenomenon under investigation. Another difficulty is raised by phenomena that are arguably outside the scope of empirical investigation. Here's an interesting example given by John Norton in his paper, Replicability of Experiment. There have been some studies examining the efficacy of intercessory prayer. In intercessory prayer, a person prays to a deity for help in everyday affairs. Usually, they will ask the deity to help heal the sick. Now, it looks like there's a fairly straightforward way to test this. We can examine groups of sick people who were the subject of prayers, groups of sick people who were not, and then just see if those who were subject to prayer are more likely to recover. In fact, there have been a few studies on this, and some of them have reported positive results. However, there are some scientists who are skeptical that prayer could even in principle be open to this kind of empirical investigation. Norton quotes a paper by critics of the prayer studies. They say, if prayer is a metaphysical concept linked to a supernatural being or force, why would its efficacy vary according to parameters such as frequency, duration, type, or form? The very concept of prayer exists only in the context of human intercourse with the transcendent, not in nature. The epistemology that governs prayer and all matters of faith is separate from that which governs nature. Why then attempt to explicate it as if it were a controllable natural phenomenon? Even if there is a way of communicating with a deity, and even if that deity does intervene in response to prayer, there's no reason to expect that this intervention will manifest in the experimental outcome, that is, in the statistics of recovery rates. So suppose, for example, that we have 100 people praying every day for patient A, and we have only one person praying only once for patient B. Well, I mean, look, it's not as if we're dealing with a drug that can be expected to elicit a specific response at specific doses or that will interact in specific ways with other drugs. As theists see it, the point of religion is to develop a personal relationship with God. But if we're dealing with personal relationships, there's no obvious reason why a deity would put greater weight on the group of 100 people. So, I mean, like, by comparison, suppose that you were considering where to donate a large sum of money. And like you come across 100 people who argue endlessly that you should donate it to charity A, and then one person suggests you should donate it to charity B. I mean, if these people have any influence at all, it will likely depend on your personal relationship with them. Like, if the people arguing for charity A are just a bunch of strangers, or maybe they're a bunch of, like, I don't know, religious zealots that you really dislike, whereas the person suggesting charity B is a close personal friend, you're probably going to be, you're more likely to be swayed by the friend, by the personal connection. The effect of praying to a deity is going to be even more obscure because we have so little understanding of what exactly the deity would want, or how a personal relationship might manifest from the deity's point of view. So, I mean, like, if this way of thinking about prayer is correct, then even studies of prayer that meet all of the 6 conditions might not be taken as replicating a finding of the efficacy of prayer. So if one team finds that prayer does have efficacy, and then the second team claims to replicate it, we just might actually just dismiss all of these studies as having no kind of inductive force. Right, well, that's it. That's it for this video. I hope you found that interesting. Goodbye.